It's a great pleasure to be here. I'm Letícia. I'm a first year PhD student at Carnegie Mellon University in Pittsburgh, Pennsylvania. And today I will be talking about solving the Schrödinger equation with Julia. So first announcement, if you want to find me or talk to me, you can find me on Julia's Slack. You can go to my GitHub to check the codes for my work and my independent track of research with Julia. And you can also open issues, suggestions on my GitHub or find me on Slack. I'm always happy to chat. So what is the Schrödinger equation? It's in the title of my talk, but I didn't explain yet. So let's start from the beginning. The Schrödinger equation, from a formal definition, describes the behavior of a particle in a force field, or it can also describe the behavior of a system over time. And it's based on the idea of taking a physical quantity out of the wave function. And in this case, we are taking the energy out of the wave function by operating a Hamiltonian. And I will explain each element of this equation during this talk. And why is it important to know the energy of a system or a molecular system? Because this equation seems to be simple, but it's very powerful. And over the years, many researchers, chemists, physicists did research on this field and tried to understand and come with methods to solve that equation. And of course, Erwin Schrödinger, Werner Heisenberg, Paul Dirac, and Oppenheimer. So this is not supposed to be an advertisement to the movie, but if this guy did research on quantum chemistry and on the Schrödinger equation and he has a movie, it might be something important. But putting the joke aside and talking about more serious stuff, and I will give a reference to Michael talks, because from the Schrödinger equation and from the wave function, you can extract a lot of information useful for biology, physics, life sciences in general. If you take a look at this first paper, you can see that the density functional theory, one of the methods used to solve the Schrödinger equation, was very important to find and explore new drug candidates for the COVID-19 pandemics. If you take a look at the second paper, you can see how DFT and the Schrödinger equation is important to find new materials. And if you take a look at the third one, you'll see that the Schrödinger equation is important for all life sciences, biology, physics, and chemistry. Now, let's go back to the formalism itself. The equation seems to be, okay, simple, short. You have an operator, you have the wave function represented as a psi, and this wave function is an eigenfunction, and you have the energy that you get away from it as your eigenvalue. And if you operate your Hamiltonian to the wave function, you obtain the property. And this is an eigenvalue problem because we were trying to find the energy element in this equation. So the operator and the wave function depend and are modeled based on the system you are working with. So depending on your molecular system, you will have different Hamiltonians and wave functions. So after all this explanation and after understanding that you can take information useful for physics, biology, material science, you understand that quantum chemistry is all you need for scientific discovery. So from that, we can expand the Hamiltonian and the operator in the Schrödinger equation, and we split the Hamiltonian into two different operators, the potential energy and the kinetic, energy of the system. And if we write down the expressions for each of these operators, we will find the expanded Hamiltonian for the hydrogen ionic system, for a very simple and small system. We can split up the kinetic energy and the attraction between the nuclei of an atom and the electron that have different charges in a one electron term in the Hamiltonian. And the repulsion between two electrons that have the same charge, you can compute at the two electrons term. And this is important to distinguish because it's easier to compute the one electron terms than the two electron terms, because you need to expand over all the electrons in the system. So you increase your complexity in the integrals. And I will talk about the integrals later. So from this, let's take a look at what happens if we calculate this Hamiltonian and solve the Schrödinger equation for a hydrogen atom, the smallest atom in the whole periodic table. I formed the 8H2 molecule, and I calculated the potential energy surface for this molecule, and you can see how these elements in the Hamiltonian change. I didn't decompose them, but from the potential energy surface, it's easy to infer that when you have the two hydrogens very close, the repulsion is high because you have the same charges closer. So you have this peak at the beginning. When you make the atoms far away from each other, you find an optimal distance. That's the distance of the chemical bond. And chemical bond is important to our life. We're just alive because we have chemical bond in this world. And if we make them even further away from each other, you lose this interaction because the two atoms will be isolated now. That's why you have the curve becoming flat. So this is the understanding of the Schrödinger equation for the hydrogen atom and how this affects the potential energy surface for a very simple problem. But life is not easy, and our problems mostly depends on multi-electronic systems, not only hydrogens binding each other. And what do we do then? Because we need to model the Hamiltonian and the wave function for these multi-electronic systems. That's a big problem. And all of those researchers were trying to find a solution for this, even in numerical methods, computational methods, and so forth. So we start by approximating the wave function by a product of the molecular orbitals we have in our molecular system. And we will call these molecular orbitals psi. And the molecular orbitals, as we already know, are linear combinations of atomic orbitals, which is great because we know how to deal with linear combinations. In these linear combinations, we decompose the molecular orbital into the contribution that each atomic orbital in the molecule has to the overall picture of our molecular system. That is great. So we have the contribution coefficient and the atomic orbital itself. And we approximate our atomic orbital into Gaussian functions. And we know how to deal with Gaussian functions because we know that if we multiply Gaussians, we have a Gaussian. And that helps us to compute the energy and the functions over these atomic orbitals. And we represent that as basis sets. So moving forward, now that we defined each element in our Schrödinger equation, it's time to say that this is a partial differential equation. And one of the methods we use to solve it is a variational method. And there is a very specific way of using this variational method, and I will explain better now. One of the approximations we have to solve the Schrödinger equation is the Hartree-Fock approximation. So now it's important to pay attention because we will change our notation. And our Hamiltonian now will be a Fock matrix, and this is represented by NF. And now our wave function is a pseudo wave function. It's called C. And we also compute the overlap between the orbitals in the molecule, and it's represented in pink. So now we will expand each of these terms again. The Fock matrix has a new element now. It has the kinetic, represented as T, the V, representing the potential energy, and a term called P. This term called P computes the repulsion between the electrons. And when you expand each of these elements and each of these integrals, you have in the Hartree-Fock equation our new Schrödinger equation to approximate for multi-electronic problems. You have the integral over the two orbitals, I and J. And then if you take the kinetic integral, you have the same kernel, and this is important because we will use this to compute our integrals at the end. You have the same kernel as you have in the overlap integral, but you have a Laplacian operator in the middle to take out the kinetic energy. And after that, you have your potential energy, and you have a quasi-Coulombic operator, and you depend on the charge of the system, and you depend of the distance between the electrons and the nuclei as well. And you now have the P element that computes inside of it the repulsion between two electrons of the same charge. We have now the big picture of how to approximate the Schrödinger equation, important for all physical properties we want to compute computationally. And now we need to understand, what do we do with that? How do we program and code these expressions? Over the years, many different ways of computing this were developed. And we go from very simple methods based on molecular mechanics to semi-empirical methods, to DFT methods, very famous nowadays. A lot of people using DFT. I showed the examples before of works using DFT for molecular and drug discovery. And we have the first principle methods. We have what we call the ab initio methods that solve all these integrals without parameterizing them. And those are very, very expensive. And as the previous talk mentioned, they scale exponentially. And if you were to take a large system, a polymer, for example, and you are to use a quantum mechanical method from first principles to calculate, you probably won't have enough time in the universe or space in computers to store all of this. So it becomes quite challenging to use ab initio methods for large-scale simulations. And that's why nowadays people develop machine learning, develop other types of potentials. They use molecular dynamics, other methods to overcome this intrinsic problem. And thinking about that, we know already that Julia is quite performant and Julia is quite efficient on computing numerics, on computing things that are costful in terms of computations. So what I did, I developed a package called QuantumFoca that calculates the integrals that build this Hamiltonian and allows us to calculate the Schrödinger equation. And this package is well documented. It has a very cute logo. Let me put the video here. So the cute logo. A fun fact. So in Portuguese, seal is called foca. That's why I call it QuantumFoca. So it's a joke to make it fun. And I hope next year at the JuliaCon, we will have stickers for QuantumFoca, hopefully, because they're cute. And using this package, I developed a graphical user interface to interact with my package, using it as a backend. So in this graphical user interface, you upload the coordinates of your molecule or your system of interest. As I'm doing here, I will show water because I think water is everybody's favorite molecule. And you upload the XYZ files you see in the text box, and you can select atoms, you can delete atoms, and you can play around with this representation. I know you can ask me, where are the chemical bonds? This will be in the next release, I promise. And you calculate the molecular integrals, and you calculate the energy of the molecular orbitals by clicking on Start. And it's quite fast. You calculate and you visualize this. The visualization is made with WebGL and JavaScript libraries for three-dimensional visualization. This shows the interoperability of Julia to work with other languages as well, using the QuantumFoca as a backend and to do the calculations. Oh, here, if you want to use only the backend, it's also possible, which is quite cool because you can open your repo and you can use the package, you import it. And let's say now you want to calculate the integrals for benzene. So you upload as a molecule and you upload the XYZ file. So this is me trying to find the file. Yes, I found it. Great. So you see the molecule. You have the atoms, the coordinates, and these are our structures in QuantumFoca. And you can interface with atoms base. So it's great. Thanks, Professor Curtin, Michael. And you can see the atomic numbers. And if you want to calculate with STO3G, you can build the basis set for your molecule, in this case, benzene. And it will give you structures for the Gaussian basis set for each atom. And from here, you can calculate the integrals. So this is me typing, trying to do something. Let me figure out what it is. Okay. I think this video is clipped, but there is another part of the video, I think. Yes. So from here, now it's quite easy to use because you form the molecule. And after forming the molecule, you can just type overlap, kinetic, attraction, and repulsion. And you see it's quite fast. So it's quite easy to calculate the integrals. You see, it's very straightforward for the benzene. So it's very readable. It's very well documented. The documentation was written with documenter.jl, everybody's favorite package. And I want to announce that the next release will be out in August 1st. And we will try automatic differentiation. And I want to call everybody to try the new release because I like feedback on the code to make it better. And I'm implementing automatic differentiation in the SCF part and GPU support for the integrals. And that's innovative because we usually have GPU support for some of the electronic structure methods like TFT, Hartree-Fock, but you don't have the GPU support itself for the molecular integrals, because most of the packages they are parallelizable, but they don't have GPU support. So QuantumFoca will have GPU support in this next release. Before I do the acknowledgements, I think I still have some time left. I will show some fun facts. So, as I explained, foca in Portuguese is seal. And the joke behind it is also because we have a very famous package called ORCA. And I was like, can my module written in Julia beat ORCA, ORCA's module to calculate the molecular integrals? In their version 5.0, they use a module called Shark. So will the foca be faster than the Shark and the ORCA? So that's an interesting question. So I've analyzed the scaling of these molecular integrals when I calculated it in parallel for series of molecules like pentacene, tetracene, anthracene, naphthalene, and benzene. And I analyzed how this scales in one and more cores for these molecules. And you see that the behavior is quite close for 4 and 8 cores. But this is not the most interesting result. And I also analyzed for smaller molecules like ethanolamine, ammonia, ethane, methane, and water. But the interesting result is here. For the new release, I've tested the molecular integrals package against Fortran and C++ code with the same formalism that I used to implement on QuantumFoca. And for this, you can see that Julia beat both Fortran and C on this. And this is something I'm still figuring out, trying to understand the details why, but one of the facts is the architecture of QuantumFoca. And in this new release, this will be even more optimized. And I will explain the architecture in a second. Also, here I show the direct comparison for parallelization in QuantumFoca for 1, 4, and 8 cores. And the curious fact, going back to this plot, is that ORCA is the C++ comparison that I'm doing. So QuantumFoca so far in the molecular integrals part could beat ORCA, which is quite cool because the seal is that cute animal and is beating the ORCA. And talking about the architecture itself, as I explained before, I took the overlap integral as a kernel to calculate the other integrals, the T, V, and G, the repulsion, attraction, and kinetic integrals, because all of them contain the overlap integral anyways. And this helped me avoid nesting for loops, and this reduced the cost of calculating. So you can use the multiple dispatch in Julia to overload the operators in the overlap integral and then getting the results. And after that, and this was for comparison because the focus of the package is the molecular integrals implementation, but to get a property out of it. And I calculated the energy of the systems as well. And to calculate the energy of the systems, I built the Fock matrix that gives me the Hamiltonian and did a diagonalization. And then you calculate the energies, you analyze the convergence based on the threshold the user established. And then if this threshold is met, you reach the convergence. If not, you do the process over and over again, iteratively. So I would like to thank my advisor, Professor Tomasz Kowalski, my committee members. Here's my GitHub queer code again. I would like to thank the Pittsburgh Supercomputing Center and the NSF for funding the project with computing hours. And yes, I leave you with the demonstration again. Thank you.
Okay, we have a few minutes for questions.
Thank you very much for the talk. How big are the molecules that you can compute right now?
Sorry?
How big are the molecules that you can compute? For example, can you compute some small polymers?
Yes, I've tested on small molecules first, but now the idea is to test on conjugated systems, larger, but I don't have these results yet, but it might work as well. But the molecules are 30 atoms large. Okay. Oh, I have a question there.
There's also a package called Fermi, and this Gaussian basis. Like, it seems that you are re-implementing, or these things are in competition with each other. Is there some planned collaboration, or is there a reason? Like, how does it differ, I guess?
Yes, okay, that's a good question. I was talking with Michael about that before the talk. So one of the differences is that I implemented the graphical user interface, and I used my own molecular integrals package, and the idea is to expand that. But after talking with Michael, I also thought, how can I use Fermi's interface to calculate the self-consistent field procedure, for example, and optimize my whole environment using Fermi. So it's a very cool idea to join things and use the best we have to have good tools. Yeah. More questions? Oh, yes.
What's the algorithm you're implementing? Is it a McMurtry-Davidson?
Davidson, yes, exactly.
Are there plans to, do you know if other algorithms are going to be significantly?
The O-ohata, for example, yes. The O-ohata will be implemented as well.
But are there, I know that there are newer algorithms. Do you know if there's going to be a significantly speed up if you implement them over? I think the ones in ORCA are not the McMurtry-Davidson, right?
Yeah, I implemented the McMurtry-Davidson because it's the one implemented in ORCA, and I wanted to do a direct comparison, so I would need to implement the same formalism. And I think it's pretty efficient based on the Hermite polynomials you have expanded there. So I don't know if other molecular integrals formalisms emerge, they will get that many adoption as McMurtry-Davidson have, O-ohata. Yeah.
Thanks.
We have time for one more very quick question and quick answer. If not, let's thank the speaker again.
Okay, thank you so much.